Welcome back, folks. Still playing with phasors. If we can use Thevenin's theorem and we can use Norton's theorem, then we can do source conversions the same way we did in DC analysis. Okay, so let's do it. It looks like, here's our problem. It looks like this. We're looking for I out, and we want to do our best to use source conversions to get this down to a manageable size problem. My goal with these source conversion problems is to get it down to an Ohm's law problem, just to kind of beat that horse as dead as possible. We can simplify these circuits. Okay, so looking at this, I'm looking for anything in series, I'm looking for anything in parallel that can be combined. What I see here is two voltage supplies that are in series. Okay, those are in series. I see these two components are also in series. Okay, so since that's in series with that, which is in series with that, which is in series with that, then I can consider these two sources in series. Okay, these two components out here are in series. Wow, this gets a lot simpler, a lot faster than you would think. Okay, so I got to combine all those things. So let's combine them, and in place of these two, which I can do that math in my head pretty easily, hopefully you can too, right? We're going to place just some general impedance, and it's going to be 1 plus J1. Okay, and in place of these two, also in series, we're going to put some general impedance here. Is going to be 1 minus J1. Okay, we just write that as a box with the impedance written right in it. The voltage supplies, all right, I got a little dirty on that one. Voltages can be specified in a rectangular form. You usually won't see that, but it can happen. Okay, so here we have 2 plus J2, and it looks like we got plus minus here. And then over here we have 6, which is also plus minus. I wonder if I'm working off an old copy of this. Anyhow, we're going to draw these as a single supply, and I'm going to draw it, I'm actually going to draw it this way. I'm going to draw it that way. So this is going to be a drop of 2 plus J2, and this is going to be a drop of 6 at an angle of 0. Okay, so if it's anything more complicated than that, I say use your calculator. This one, because 6 is at an angle of 0, you might could do it in your head. Minus 2 plus J2. I'm going to do it on my calculator because I don't want to do it twice, honestly. Okay, do it once. 8.25 at an angle of negative 165. We're going to call that 166 with a skosh of rounding. It's like 165.9 something. Okay, and that's in volts. So I can replace this one. I flipped the polarity, so I'm going to have to redraw that. And I can replace this one with a single supply that is 8.25 at an angle of negative 166 degrees. Okay, so that's getting much more manageable. I want to get it down to as simple a problem as I can. So let's grab this for safekeeping. It's easier if I do it with my mouse. Let's try this. The pen is cool. The mouse can be mightier. Didn't exist back when that quote was first said. Okay, so what I see now is that this is a voltage supply with a series impedance. So this is a Thevenin equivalent, and I'm going to convert it to a Norton. Okay, So in order to convert it to a Norton, the impedance is just going to drop down. Maybe I should have just cut and paste that. Okay, so that's going to be 1 plus J1. And now it's going to be in parallel, right? And we're going to have to figure out what happens here. This is no longer going to be a voltage supply. Let me reuse it. It's going to be a current supply. Just like that. Okay, we got to figure out what that current is. We figure out what that current is by taking the Thevenin voltage, which is that. Okay, and we divide by 1 plus J1. That's in ohms, since it's an impedance. Do I still have this? It's still in my calculator. I love it. So let's reuse it and say divided by 1 plus J1. 1. There we go. All right. And that's going to give us 5.83 amps at an angle of 149 degrees. Okay. 5.83 at an angle of 149 degrees, and that's in amps. Okay. Not bad. What's in series? What's in parallel? Well, everything's in parallel now, but the things that I can combine in parallel are these two. If I combine this one with it, I'm going to lose I out, and I'm going to be in trouble. So what I would like to do now is take these two and combine them in parallel. Okay, now I should have cut and pasted. Can I get away with it? I should have cut and pasted. There we go. Look at that. Everything's turning up Millhouse. Okay. So we're going to combine those two in parallel. So we're going to have 1 plus J1 times 1 minus J1 over 1 plus J1 plus 1 minus J1. Okay, and we'll figure out what that is. I'm gonna combine it, so I'm gonna get rid of one of them here. Okay, get rid of all that stuff, and I'm gonna place that parallel combination right here in this box. Whatever it may be. So we got to figure that out. So get comfortable with the calculators, folks. If you haven't already, you're going to need to. Okay, so I'm going to do some, I'm going to store those values. When I'm working with complex numbers, a lot of times I like to store them as variables. And that way I don't have to enter them over and over again. So let's do that times that, divided by that plus that. Does that work out? I got an answer of 1. Doesn't that freak you out? I think I did it right, though. 1 at an angle of 0 degrees, or just 1 plus J0 would also work for that. Oh, let me think about that one. This one's going to be that's going to be 0.707, which is root 2 it's 1 over root 2 at an angle of positive 45. This is 1 over root 2 at an angle of negative 45. Okay, so that angle is going to be 0, and it's going to be 1/2 in the numerator, and then this is going to be, the imaginaries are going to disappear, and I'm going to have 2, and I'm going to divide by 2. Is it really 1/2? Stand by, folks. When in doubt, throw MATLAB at it. It agrees. We're going to call that good enough. I'll try not to do mental gymnastics with complex numbers. If I can avoid it, certainly not when I can just fire up MATLAB and do my thing. Okay, so let's see. So that's 1. Ha, cool. Oh, wow, that makes this easy. Who made this problem? It's like I pulled it out of a textbook at some point or whatnot. Okay, so what can we do now? We've got a Norton equivalent, and you know, you could go right to a current divider, you could do mesh, you can stop at any point when you're doing source conversions and do circuit analysis. But I want to 100% this game, so we're going to say this is our Norton equivalent, and we're going to turn it back into a Thevenin equivalent. Did I copy the circuit? That would be awesome if I did. It's a beautiful day. I should go for a walk. Okay, let's do this. Copy the circuit. Get all that notation back on there. There we go. Turn it into a Thevenin equivalent. So what that means is we're going to get rid of this. We're going to turn the current supply into a voltage supply. That can be a little orange. And we're going to take this 1 ohm and we're going to get rid of it. And move it up here. 1 at an angle of 0 degrees. Okay, now what's the voltage supply? Well, the voltage supply is 5.83 at an angle 5.83 at an angle of 149 degrees. That's in amps, and we multiply that by 1 at an angle of 0 degrees. That's in ohms, and we get 5.83 at an angle of 149 degrees, and now it's in volts. Okay, so we can grab that. That's our Thevenin voltage. So we can slide that in. It's too big. We can slide that in right there, and then we can do some union wiring. That looks like that. Okay, almost there. I want to get it down to Ohm's law. What's in series, what's in parallel? This is kids play now, right? This is in series. So we can just add them together. 1 plus 1 is in fact still 2. And I of course forgot to copy the circuit, but I think I can draw this one. Stand back. Okay, so this is going to be a, let's pick the color I want, 5 plus 5.83 at an angle of 149 degrees. That's in volts, plus and minus there. And we can combine these two into a 2 at an angle of 0 degrees. That's in ohms. Okay, because we're not going to lose I out since they're in series this time. All right, what's I out? It's 5.83 at an angle of 149 degrees over 2 at an angle of 0 degrees, and that's in ohms, volts. And let's see what it is. All right, so let's call that 2.92 at an angle of 149 degrees, and that's in amps. Okay, so there's your final answer for the problem, but the real lesson is the journey, right? We got how many meshes? Let's play this game one last time. Meshes and nodes. Right? Because the whole goal here is to reduce the complexity of the analysis, and we can do that by reducing the number of meshes and the number of nodes. Okay, so we have 2 meshes, and we have 1, 2, 3, 4, 5, 6 nodes. Okay, just doing some simple combinations, we got down to 2 meshes and 1, 2, 3 nodes. So that alone was a big move. Okay, and we went back up to 3 meshes and down to 2 nodes. Okay, when we got down to this one, where were we? 2 meshes, 2 nodes, 1 mesh, and 1, 2, 3 nodes. Okay, and then down to here, our favorite, 1 mesh and 2 nodes. Okay. Source conversions, it's magic. We can do them with complex numbers. I didn't have to do any differential equations, and I found the answer to my problem. I thought I was going to make this my last problem. I think I'm going to do a little simulation for you, because all of this can get a little deep, and you lose touch with the signal going in and the signal going out, and tying it back to the time domain plot that we would see on the oscilloscope. So I think I'm going to find a problem, I'm going to work the analysis, and then I'm going to simulate it, and we can see, using LT-Spice, we can see the time domain plots that we anticipate from the analysis, right? Because if you're going to make an argument, you should always calculate, simulate, and prototype. We can't prototype right now, so at least we can try to simulate. Okay, that will be the last phasor problem, and then we move on to new stuff. Stay tuned and good luck.